Oh, I don't know where it went.
Well, you had it this morning.
I know I had it this morning. I lost it. I don't know where it went.
Okay.
I'm sorry.
You should be. No, it's. Was I still this period for you?
Yeah.
Okay, then you're fine. Let me pull. Where did I leave my mouse?
Are you recording?
Yes.
Are you mic'd up?
Yes.
Yeah, you're gonna see it.
Where is my? There it is. All right. So, am I recording? Yes. Am I mic'd up? Yes. Why am I recording? Might be a better question. So I will often do that so that I can post it as a resource for students that might have missed. So if anybody is absent on a day that I'm giving like in-depth instruction, they can tune into it later. Does that make sense?
Yeah.
They can watch it later. Any questions about that? Is that all right with everybody? Yeah. If any student ever ends up on camera, notice it's pointed this way, not that way. But if any student ever ends up on camera, they're not going to end up published or on YouTube or something. That has happened a couple times, but I specifically asked those people, hey, is it all right if I leave you in there? Because it was good, right? So, and I check Infinite Campus, because some folks have like do not publish, do not photograph orders on there. So I do try to be careful. All right, in Infinite Campus, I am pulling your class up. Give me a moment. And we're going to do two things at once. We're going to take attendance on this paper, because we're still doing paper attendance until Monday. And then I'm also going to, as I call your name, hold up with the signature facing me so I can see if you got that signed, okay? So here we go. The lesson. So I'm going to pull the curtain just for a moment so you can see kind of the behind the scenes. A lot of work goes into this. I don't just pull things out of thin air most of the time as far as the schedule and whatnot. I have first, second, third, fourth quarter planned out as much as you can because we will have to adjust based on how quickly you're learning or other things that are interrupting. But you'll notice like right there's the first lesson. And I have all these planned out. Color coding is a thing on here. You guys don't need to know everything, but I'll tell you the green aren't actually specified. Like this is clearly this science standard. Okay? But those lessons are going to help you kind of like if you don't know this, you're probably going to struggle with the standards. Does that make sense? Okay? So the red ones are standards for you, and they have been identified by the science department as like you really need to know that. Like we don't want you to leave here without knowing that. Is that true for all the standards? Oh, of course. But we will spend extra time to make sure you know the ones that are red on this spreadsheet. The yellow ones are regular standards. Like this one, it's about eclipses, okay? One of your standards makes you gotta know that there's phases, right? Orbital dynamics, a little bit of that. So it helps with it. And then you'll see there's some that are grayed out. Well, there's a lesson on eclipses, and they talk about solar and lunar eclipses, and then there's a lesson on solar eclipses and a lesson on lunar eclipses. I don't need to go that far into the weeds with you all. This one is good enough. So there'll be some that we just skip. There's also some stuff on here that's not even CK12 lessons. Okay? So some stuff that I want you to know, or our standards, isn't covered by, or isn't covered the way I would prefer you to be covered by CK12. So we won't use CK12. But it is our most common resource. Does that make sense? Online textbook. And here we go. So if I were to click on this very first one, it's going to open this up. How many of you all is this the first time you've ever seen a CK12 lesson? What? So how many of you have already seen it? Everybody? Okay, wow. What class? And which? Jewel used it? Really?
With a few things, as
That's cool.
just as articles and stuff for us to read.
Okay, that's neat. So I used to work with her. I started using this after I left that school, so it's kind of neat that we both kind of found it and are using it now. That's cool. So here we go, 1.2 scientific method. This is physics for high school. The physics for high school is physics for high school. Some of it is going to be pretty easy for you all. Some lessons are going to push to full-on physics. So we will apply the brakes where we need to. Like, okay, we're getting in a little deep type thing. Okay. This lesson's totally fine, 100%. I don't think any of you will be learning anything here for the first time in this lesson. But you might be tweaking your understanding. Today I've asked questions and some people are flat out wrong. So they didn't remember. Okay, so pay attention. Here we go. It says Don Fraser, a NASA chemist, is conducting an experiment with a laser imaging system. It does not say what he's doing exactly, but he's conducting an experiment. Very cool. Do you have a problem? Is that seat going to be a problem for you? I anticipate it will be. Prove me wrong, please. Okay. Would someone like to read our first paragraph? I'm going to grab this microphone and I'm going to toss it at you. All right.
That whole paragraph, that one?
This whole paragraph right here.
In science, we need to make observations on various phenomena to form and test hypotheses.
Stop! Right here, if I hover, sometimes CK12 anticipates that you might not know something. If they anticipate that you might not know a word, they highlight it in green and you hover and it gives you a definition. So read that definition for me.
Hypothesis. Tentative explanation to scientific question that can be tested.
Okay, so earlier today, I said, before I put it on there, I said, what's a hypothesis? I heard things like, it's an educated guess. I heard things like, it's a theory. Ooh, pump the brakes on that one. It is kind of like an educated guess. Tentative means like, right? But specifically, it can be tested. Continue. Oops, sorry. Help if I wasn't in your way.
Some phenomenon
Phenomena, plural.
can be found and studied in nature, but scientists often need to create an experiment. Experiments are tests under controlled conditions designed to demonstrate something scientists already know or test something scientists wish to know. Experiments vary greatly in their goals and scale, but always rely on repetitive procedure and logical analysis of the results. The process of designing and performing experiments is a part of the scientific method.
Awesome. When someone is reading for the class, whether it's me, whether it's a student, you're reading along, right? All right. Scientific method is a process used by scientists to acquire knowledge and improve our understanding of the universe. It involves making observations on the phenomenon being studied, or phenomena, if it's more than one thing, right? Suggesting explanations for the observations, testing those possible explanations, also called hypotheses, by making new observations. A hypothesis is a scientist's proposed explanation of a phenomenon which still must be tested. Okay, so here you go. Scientific method right here. You guys can put this in your notes. By the way, you should have your notes out. Everybody got your notes out, right? Everybody has their notes out? Because if you didn't know what a hypothesis was, or you thought you did, and you're like, oops, you probably want to put the real, a more correct understanding of that term in your notes to help you grasp it, to help you learn it. So hypothesis, a tentative explanation to a scientific question that can be tested. If it can't be tested, then it is just an idea you have. If you tweak that idea, if you figure out how to test it, then it becomes a hypothesis. So a hypothesis is an idea you have that can be tested. A hypothesis is an idea you have that can be tested. And you can word that however you want, as long as the gist is still the same. Does everybody know what a gist is? It's the basic idea, right? So the scientific method, you've seen this before. It might not have been exactly written this way, but you have a problem. You made an observation. You saw something, and you're like, whoa, that's a head scratcher. What did I just see happen? Why did that happen? And so it's an idea, and you start to form the idea into a statement. It might sound something like this. I think if this, then that. Right? And you can fill in with the other words. I think if this happens, then that will happen. Or I think because this is happening, that is happening. Does that make sense? Write those words down. If this, then that. I actually have it on the I can statement for today over here. You can understand that if then, or if this, if this, I guess it would still work without that word there, but if this, then that. You can understand how that works within the scientific method. So, you have the idea, you say, if this happens, then that will happen. Okay, prove it, right? So we design an experiment to see if we're right. Everybody tracking? Okay. And we run the experiment. We conduct the experiment. At the end of the experiment, we're watching it happen. We're making observations of our experiment. And we're recording those observations. We're taking measurements, perhaps. We're seeing what the result is. We analyze what is happening. And then you draw what? You draw conclusions. You start thinking, was I right? And it might be really obvious right away. It might not take much thought at all. But it might take a little bit of measurement and careful analysis. But sometimes it's real quick. Oops, I was wrong. Or, yeah, I had it. Yes! I was right. And it's really nice being right, isn't it? Doesn't it feel good to be right? So you had an idea, you designed an experiment to test it, that makes it a hypothesis. You experimented, and you either confirm, or you say, oops, nope. Okay? This diagram says, hey, if the data from your experiment confirms your hypothesis, so if yes, you should go right back and test it again. So you probably run the experiment again to do what? To double check, to make sure everything is legit. Okay? If it is, your confidence level goes up. Maybe you design another experiment. If you can think of another way to confirm your hypothesis, design another experiment. Do that one. If that one confirms your hypothesis, okay, now we're on to something. Okay? Does that make sense? We're like getting kind of excited. I've tested it 2 different ways, maybe more, and we are right. What period are you in?
Huh? Oh, that was moving the office. Yeah, I dropped off there.
Thank you.
Yep.
What would you do next? What do you think? You, on your own, I mean, sure, you did some research, you gathered data, right? We poked around, see if other people already had the problem. They might have already solved my problem, but assuming they didn't, I had to keep going. What next?
Write a data report on like what you found.
You're definitely going to write a report. Okay. If you're a serious scientist, you're going to write a report.
Like a full conclusion.
Yeah, the conclusion. So it's going to be a scientific paper. Guys, a scientific paper is the whole thing. You say, hey, here's the problem I saw. Here's the observation I made. Here's the idea I had. And then I designed this experiment. And these are the specific steps to run this experiment. Here are the observations I made during the experiment, the data I collected from the experiment. And then here is why I think, this is my conclusion and why I think that. Does that make sense? You're being very detailed, absolutely. But you write a science paper for yourself, okay, sure, to organize your thoughts, save it for later. Why else do you write a science paper?
For other people.
For other people. S word, you're going to share it. You're going to share your work, okay? It's working. How many of you guys have ever created something and you saw nothing wrong with it? You might have even waited a day, looked back at it again, fresh eyes, right? Looked at it again, saw nothing wrong with it. And you turn it in. Guess what your teacher does? They see what? They see the mistake. That you looked right at it and you didn't see it. Have you ever looked right at a mistake and not seen it? You can look right at something and just not see it. Especially if it's your own work. Because when you're writing it or when you're typing it, it totally makes sense in your head. You might think a word but not type it in. Right? That sort of thing. Same thing with the scientific community. You can't do it by yourself. So you do the whole thing, sure, you might ask for help in-house too. If you've got people you work with closely, you're collaborating with it, then you're still going to publish that. You're going to share that so that your peers or near peers can confirm. They're going to look for mistakes. They're going to look to confirm or deny that your hypothesis is true. They might think of other ways to test your hypothesis with different experiments. Does that make sense? Okay, so that's why we go back to test the hypothesis again. But over here, our diagram on this resource says, well, if it doesn't agree with your hypothesis, your experiment says you're wrong, you should just go right back and make up a different idea. You're proven wrong, go back to the drawing board, come up with a new explanation, a new hypothesis. You might have to do that, but you should not go straight here. Can somebody tell me what I'm thinking? Instead of going right here, saying, well, I got it wrong, throw it out, back to the drawing board. Go.
Try it again.
Try again. Maybe you made a boo-boo, right? Go back, run the experiment, just like you did to confirm, to double check that you were right. You should also double check that you were wrong. Run the experiment again. Make sure you didn't mess something up. Maybe the second time it confirms your hypothesis. Maybe there was an error in the way you conducted the experiment. Here's another thing. Let's say you do decide, I ran it a couple times, it's wrong, I was wrong. What should you do with that data if you're a good scientist?
Post it.
You should post it. You should share it. Just like you shared that your hypothesis was confirmed on your end and you want people to double check it. Hey, this is what I thought. I'm pretty sure I'm wrong. I ran these experiments and it looks like I'm wrong. Publish it. Share it with your colleagues. Share it with your peers, because they will still, somebody is going to look at your paper and be like, well, that was a pretty good idea. What was wrong with this experiment? And they're going to look at your procedures. They're going to try to recreate it. They're going to see if you made a mistake. They're going to see if they can maybe conduct an experiment that supports the hypothesis. What's going on here exactly, okay? Now, that's great. So we had an idea. We designed a way, we wrote it in such a way that it could be testable, so it becomes a hypothesis. We actually do the test or experiment. If yours confirms it, everybody else's confirm it. If it's been out there for a while, people have put it under scrutiny. Have you ever heard the word scrutiny before? Okay. They have really evaluated it. Put it under the microscope, so to speak. And no one has been able to disprove it. And everybody seems to be agreeing based on evidence. That's key. based on evidence, everyone's agreeing. Yes, the evidence looks like this. Even if in the back of the mind, they're like, I don't know. Hey, if the evidence points towards it, and you don't have any evidence to counter it, if you don't have an experiment that disproves it, that hypothesis graduates. It becomes a theory. Once it is a theory, once that idea has gone through those steps and it is become a theory. By the way, it might have been combined with some other ideas that were tested to form that theory, right? But once it's a theory, can it ever be overturned?
Yes.
Very quickly. Sometimes it can happen really quickly. If somebody designs an experiment and they can prove that theory to be like that doesn't work. Done. Over. Okay? And then you are kind of back, well, okay, but we still have all this supporting data. What's the new explanation? How do we explain what we are seeing now? Because we had this one experiment, like, okay? So here we go. Theory versus law now. So I'm hovering, broad explanation. A theory is a broad explanation. And you can underline or circle the word broad. Or you could change the word. A synonym in this case would be general. A broad or general explanation. It is not specific. A theory is a broad explanation of what's going on. It's widely accepted. Widely accepted does not mean 100% of everybody believes it. Okay? It's not about convincing, it's about evidence. Okay? You might doubt something, but if you don't have evidence to disprove, then it's still a theory. So a theory is a broad explanation that is widely accepted because it's supported by a great deal of evidence. Whereas a law is an explanation that always applies under specific circumstances. So again, theory is broad and general. Laws are specific, based on large volumes of evidence and no known exceptions. It is definitive. It is certain. See the difference? It says right here, theories can never become fact or law. Oops, nope. Theories are general or broad. Laws are specific. And I'll be honest with you, if you want to get into the weeds and do semantics, which is wordplay, like, well, if a theory is around for a long time, no, they're not trying to do the same thing. So sometimes I think people, including myself, like, well, if it makes sense, if it's around a long time, doesn't it become, no, can't be, because they're not doing the same thing. One is general, one specific. All right, in science, a law is a mathematical relationship that exists between observations under a given set of conditions. So there's another definition of a law for you. Math. Math can prove stuff, can it?
Yeah.
Math works in a specific way under specific conditions. When we learn about and do the math for Newton's universal law of gravity under specific conditions, it works every time. The math won't lie. Does the law of gravity apply, though, the same if you're near a super heavy object like a supermassive black hole? No, but in a specific case, every time it's going to behave the same way. On Earth, Earth maintains a pretty steady mass, yes? Does Earth gain or lose mass? Yeah, but relatively it stays about the same. A human person, average human person's going to be about 150 pounds, okay, adult. If you take the mass of those two objects at a certain distance, the force will be the same. You can determine the force. There's an activity. I don't think it's working right. I think there's a glitch in the program, unfortunately. If you go in here to launch, you can play with it, see if you can get it to work. Maybe it's a glitch on my end, or maybe just one or two. But you answer some questions by clicking "Challenge Me," and I'm showing you this. If you get it to work, great. But other simulations that we come across will work similarly. You do the challenge, and then you'll come over here and you'll be able to adjust certain things. Like right here, I can adjust the size of the wheels. I can take different weights and put it on the skateboard, and I can adjust other parameters in the simulation, like the steepness of the grade of the ramp. I don't think I've ever had anybody get this to work. So if you want to play with it, see, maybe do the questions first. Maybe that would unlock it somehow. I've never seen it work. Okay. Summary. On every CK12 lesson, close your laptops. I told you to close your laptops. I never told you to open them back up. On every CK12, there is a summary with bullets, basically saying, hey, these are the main points of the lesson you just went through. You should compare that to your notes and to what you know. If you know one of these bullet points very well and you didn't put it in your notes, is that okay? Sure. If you don't know one of those very well, you probably should have put it in your notes so you can study it, look back at it later to reinforce that content. Okay? So you'll want to look at all these. Then there's going to be review questions. We'll go over those. Often we will go over these together, especially if there's math. If we're using formulas to do math or whatever, we will do those together before, well, and there might be a video, before you'll go, see where mine says view practice right here? I know if you've already done CK12, you know how this works, but for those that haven't, yours would say start practice, and you'd click that. Now, you're going to go into those questions. There's usually 10 questions. You're totally allowed to get out of them and go back into the reading and find the answers, aren't you? Okay? Please don't guess. Take your time. Find the answer. Do the math if that's what you're doing. And then when you're done with your questions, you'll scroll back to the top. I think you have to go all the way back to the top. And where mine says class insights, because I'm on the teacher end, yours would say turn in. And you click to turn it in. Everybody understand? A few of you will not do that. I'm anticipating it. We'll get there. We'll figure it out. At this time, I'm going to go assign. I'm going to go to Google Classroom. I'm going to find your class right here. I'm going to assign it and make it due on Tuesday. Monday, when we come in here, we are going to watch the video. You do not have access to it because it's YouTube video. I have to see if I can request that to be unblocked. So until then, we're going to watch the videos on the big screen. Does that make sense? So we're going to do that. Right now, when I assign this, right now, click. You guys can look over the summary. You can look back over it. You can look at pictures. You can try to play the videos. Good luck. And you can check your notes. Okay? Monday, don't do the questions yet. We haven't finished the lesson. Okay? If you want to take a peek at the questions, I won't stop you. I won't get mad at you. Okay? But Monday, we'll watch the video, and then I'll have you guys answer the questions. Okay? And we'll probably look at the review questions together first, too. Good? All right. Check for me. Go open up your computer. Check for me. Make sure that posted. You can take a peek at the questions. You can look at the summary. Make sure you have everything you think you need in your notes. Remember, scientific method, idea, if this, I think that will happen, or I think because of this, that will happen. You got to design a test, confirm or deny, repetition, sharing, that might become a theory, theories can certainly be shot down if they're disproven. They can be disproven. I'm going to do a Google search. I want to come up with a couple of good examples. I'm going to say, hey Google, what are some famous theories that have been disproven? That might be fun. Okay. So here we go. Really good, well-known example. I'm sure you've probably all heard this one before. Geocentricity. So based on observations, scientists, astronomers, took what they saw, did whatever math they thought they needed to, and they came up with a hypothesis, which is an explanation for their observations. They said, I think, based on what I'm looking at, the Earth is in the center of the universe. That's geocentricity. The Earth is in the center, and everything orbits around or is centered around the Earth. Later observations and mathematical explanation disproved that. And at first it was, well, no, the sun is at the center of the universe. Was that disproven? Yes. Not the center of the universe, just the center of our little local universe, so to speak, right? Our solar system. Okay. So that's a really good example of a theory. They had hypotheses, they processed it, everybody was like, let's take our own measurements, and they all, the consensus at one point was the Earth is the center. Disproven. Spontaneous generation, this one says. What on earth? The spontaneous generation of life just pops into existence. That one was disproven. Louis Pasteur. Have you ever guys heard of the process of pasteurization?
Yeah.
Yeah? So, like, for example, the milk that you drink. Unless you're at a dairy farm and you just take it straight from the milk tank, the bulk tank. It gets pasteurized, it gets boiled, right? To kill any pathogens that might be in it. So Louis Pasteur's work helped to disprove the spontaneous generation theory. What else? Huh? Let's see. What other ones do they have here? Luminiferous ether. Good grief, what's that one? Luminiferous ether became the answer to what question? It was the medium that light traveled through, an invisible substance all around us that couldn't be felt. No, that's been disproven. You can have a near-perfect vacuum. You don't need a substance for light, for example, to pass through it. Radiation, right?
Yeah.
Radiation doesn't require a physical medium to pass through. It can go through a vacuum. Cool. Anyway, there's a bunch more. That's a kind of a fun search. How much longer we got? 39. You got about 6 minutes? 5 or 6 minutes. Do not pack up. Do not pack up until a minute out. Please. Make that the standard in here. You guys keep poking around. I see somebody cleaning up their notes. I see you're already packed up. You say, well, I haven't put the computer away, but it's closed, right? So, take a look. What are some famous theories that have been disproven? It's kind of fun. Nerd out.